I hope that you'll have a wonderful time visiting us at Stony Brook, and that you'll find this mathematically informative week and a half. It's a great pleasure to introduce our first speaker for the workshop, Mr. Simon Donaldson, and he will be speaking on, he will be giving you an introduction to differential geometry on toric varieties.
Thank you. So this morning I'm going to give a talk on rather standard material about, as in the title, geometry of toric manifolds, or more generally toric varieties. Then in tomorrow's talk I'll talk about some of the more advanced and specialized things about proving existence theorems, and both known results and open problems. Just looking for them. Well, we got some small bits.
But I actually don't think that that's. So let's see if we can talk.
So before beginning talking about this toric situation, let's just briefly mention a more general context. Because this will, for one thing, be relevant to some of the other lectures in this meeting. If we're studying scalar. So we're studying calorimetrics on some manifold X in a fixed cohomology class. Then one interesting aspect of this is that the space of all calorimetrics of this kind has itself an interesting geometry, which is an infinite dimensional space, which is very much analogous to the space of positive definite Hermitian matrices. Say K by K matrices. So on the one hand, this thing is a cone in the space of all Hermitian matrices, which we can think of as R to the K squared. So it's a cone, a convex cone. On the other hand, we can think of this as a symmetric space. We can, because any two positive different Hermitian matrices are equivalent under the action of the general linear group. So, the stabilizer of one of them, if we take the standard positive form, the stabilizer is the unitary group. So we can also think of this space of matrices as this homogeneous space, and in fact this is a symmetric space. So these are essentially different geometries on the same space of matrices. The sort of and the same thing is true for these, or the analogous thing is true for these calorimetrics. If we think of these in the standard way, we could think of parameterizing these by a Kähler potential. So we take omega naught plus I d bar phi. So we require, of course, this to be positive. So this is a convex condition on the Kähler potential. So we can think of this as a convex cone in the space of the functions. So this is the kind of standard complex point of view. But another point of view is to say that if we think about such a Kähler metric, we can think about. I mean, we have three different structures. We have a complex structure, we have a Riemannian metric, and we have a symplectic form, which are all any two determine the third. If we just focus on the symplectic form, then it's a basic fact that within our deformation class, any of these symplectic forms are equivalent. So we can think of we have a fixed once and for all standard symplectic form, and then varying the complex structure. So from a different way of setting things up is to define so at each point P in X, we can define a space, say J sub P is the compatible complex structures on the tangent space of X at P, compatible with our fixed symplectic form. And so this thing defines a fiber of a bundle, say script J over X. And then we can think of giving at least an almost complex structure compatible with the symplectic form is giving a section of this bundle. Of course, if we're interested actually in Kähler metrics, we'd be interested in a particular subset of these almost complex structures given by the ones that are actually integrable, the actual complex structures. In any case, from this point of view, what you see is a natural symmetry group coming into play, which is not really visible from the other point of view, but we have an action of the space of symplectomorphisms of X with respect to this fixed symplectic form acting on this space of sections. So say G is the symplectomorphism group. Acts on the sections in a natural way. So you should think of this group here as the analog of the unitary group in this discussion of the space of Hermitian matrices, positive definite Hermitian matrices. And in fact, one can develop this point of view to argue that in a formal way, the space of Kähler metrics could be regarded as a symmetric space where we could introduce a mythical complexification of this group in general. And the space of Kähler metrics write it as, say, GC over G, by which I mean that this complexified group doesn't actually exist, but nevertheless the symmetric space structure which it would have if you would have if it did exist is something that one can define. So in particular, there's, for example, a notion of geodesics in the space of calorimetrics, which would correspond to the standard definitions one would introduce in this setup, essentially corresponding to one-parameter subgroups in this complexified group. But the geodesic condition is something one can write down and is essentially a homogeneous Monge-Ampère equation. So this is really background to the present talk, so I'm not really going to take it much further. The same, I think the same things will appear and be developed further in other lectures. I should say this goes back to Mabuchi, these ideas. But the point I want to bring out for the purpose of this lecture is that in this general situation, one has this sort of abstract picture, which is helpful, but it is it is hard to work with. This second point of view, say, is somehow hard to work with because we don't really have, in general, this group. So although one has a kind of a formalism, it's somewhat perhaps of limited use for that reason. So the point of this toric situation is that when these difficulties go away, I will explain, and one does really have these two different pictures, the complex and the symplectic picture, which one can use to study the differential geometry. So that's what I want to explain today, part of what I want to explain today. So to say toric, in the toric case, all this is much more, say, visible or transparent. So let's begin then with the standard sort of theory about these toric manifolds. So say 2, the standard theory. So just to be precise, what do we mean? We want to say that we're going to consider a compact Kähler manifold. This is what we of a complex dimension n, and we want to consider a effective action of an n-dimensional torus by holomorphic isometries. So Tn, S1 to the n, acts effectively, not just the trivial action, for example, by holomorphic isometries.
Zero.
I might say so. Let's often we'll restrict to the case when, so to avoid this point that Claude mentions, let's also put as part of our definition the condition that in fact our Kähler form, omega, arises the curvature form of a holomorphic line bundle, and we can lift this action from X to an action on this line bundle. So we have a Tn equivariant line bundle with curvature minus I omega, I should say. We could get a slightly more general concept by relaxing this condition, as we'll mention in a moment. But this is really, for most purposes, a natural thing to assume. So one of the attractions of this topic is that there are many different ways of thinking about this, and different ways of developing the theory, which we'll outline in a moment. Some of these, but what is the, whatever way you take, what is the conclusion? The conclusion is that such things correspond to certain polytopes in Rn. So the basic correspondence. Such data correspond to polytopes P in Rn. So we think of this as Rn with a standard integer lattice in it. So these are the crucial thing is that these are going to be convex polytopes. So in the case of, we'll mostly think about the case of n equals 2, we would just mean some sort of polygon. So defined by a finite number with a finite number of faces, but with certain integrality conditions. So for what we've got, I think this will be called an integral Delzant polytope would be the right terminology. First of all, we want the vertices to be lattice points. So another way of saying it is that P is the convex hull of a finite number of lattice points. And what follows from this that we can think of P as defined by a finite number of inequalities, so lambda R of X is bigger than or equal to CR, where these are what integral coefficients. So more precisely, this is what's called the Delzant condition to consider polytopes defined by integer inequalities rather than just real ones, but also we want an integer, so the what are they called? The vertices are integral. So in fact, if we it's only having the vertices integral that gives us this line bundle. If we relax the requirement that we had this line bundle, if we just ask for this to be a Hamiltonian action, then we would just have this first condition. So that's to say, it's i.e. P is the convex hull of a finite number of lattice points.
said.
Right. So I haven't finished saying. So what the final crucial thing is that at each vertex, or near each vertex, P is defined by without relabeling these lambdas, say lambda 1 beginning to C1, lambda n beginning to Cn, say, where the lambda I form an integral basis, where these things an integral basis for the dual of our lattice. So what that means is if we just look around any of these vertices, see the picture here, then we can find a transformation by SLNZ, which takes this picture to the standard picture, where these are just given by the standard coordinate functions, and we just map to the standard sort of positive quadrant. Yeah, so this is really the crucially the Delzant condition. If you relax this, then you would be getting not manifolds but more general sort of singular, mildly singular spaces. So we said there are various ways of thinking of this correspondence, right, setting up the correspondence between these n complex dimensional manifolds with all this structure, these actions and so on, and these polytopes in Rn. So one approach, say the complex approach, so let's leave aside the line bundle for the moment. Just think about constructing a complex manifold for simplicity. Supposing we have such a setup, a manifold with a holomorphic isometric Tn action, then the action will extend to a holomorphic action of the complex torus. So Tn C star to the n must act holomorphically. And since this has got the same dimension as our manifold, pretty clearly it's going to have an orbit which is an open dense set in the manifold. So the orbit open dense. So we can think of constructing our manifold as a compactification of this C star to the n. The basic example would be if n is 1 and x is just going to be the two-sphere. So of course, our torus is now just the circle acting by rotating the two-sphere in the standard way. But we can extend that to an action of C star, and the orbit is just given by the standard. If we take the orbit of 1, that's just given by the, thinking of this as CP infinity, CP1 in the usual way. We can think of this as C star union 2 extra points, Donaldson infinity. So we have to construct our compact manifold, we take this open dense orbit and add on these 2 points. And we can do that in this general situation. We can do that where the crucial thing are these matrices which compare. So if we have these matrices for each vertex, we have a matrix in SLNZ which compares the basis of defining functions at that vertex with the standard one. So if we take any 2 vertices, we have, by composing those, we have a matrix which takes one set of comparison to another one. So we have a vertex, say, label alpha, and a vertex, say, label beta. Then we have some G alpha beta, say, in SL NZ, which takes the set of defining functions here to the set of defining functions here, after we've chosen an ordering of some choice of ordering required. But we can make this act on C star to the n just by changing, sort of going from multiplicative to additive notation. If we like, we act on, imagine for the moment we can take logarithms, so we're going to act by saying that the log of, after we transform, say, z primed a, is going to be G alpha beta AB, sum of the log of z b. So we're just allowed to take logarithms to go, we can just take the standard action of this G alpha beta on that.
Set A and set B are coordinates in C star.
That these are the coordinates on C star to the n. So I'm just saying if we just imagine we can take logarithms to make this Cn, then we're just taking the standard action. But if we take this formula, then exponentiate to remove the logarithms, then we'll just get the corresponding multiplicative formula. So it's going to be the product of ZB to the G alpha beta AB. So this is, because these are integers, this is actually well defined. So what we can do from this point of view, for each vertex, we take a chart isomorphic to Cn, and then we're going to glue these charts over the copies of C star to the n contained in them using these maps. So we glue over C star to the n. Using these maps. The basic example here will be for each, what is the standard way we construct the two-sphere? We take two copies of, we take 2 copies of C, where coordinates say Z and Z primed, and then over C star, we identify z primed is z to the minus 1. Of course, the usual way we do this. And that would just be the simplest case where we have, so this case, of course, the p is going to be just the interval. In R, we just have one of these maps, G alpha beta, which is just minus the identity, and this is the corresponding multiplicative formula. So we just have alpha beta, G alpha beta, is minus 1. So this is one approach. We construct a complex manifold just using the combinatorial data of these integer matrices. We haven't discussed the line bundle here, because in fact that's an extra requirement. We're not using in this. So far we haven't used the fact that these are integral vertices. We're just using the del Zang condition. So another point of view is to think about constructing, first of all, a symplectic manifold. So we could start from this point of view and just forget about the complex structure and just talk about, we have a symplectic manifold where the symplectic form is the curvature form of a line bundle, and we have this we have this action, and the line bundle is an equivariant line bundle. Then one standard fact then is that the fact that you can lift to this line bundle means that the action is Hamiltonian. So as to say we have a moment map mu from x to Rn, and a basic theorem of Atiyah, maybe Gilliman and Sternberg, is that the image of this, in this situation, the image of the moment map is a convex polytope. So this moment map just means, if you like, we've got S1 to the n. For each circle action, we have a Hamiltonian, this is the same content, and we can put all those Hamiltonians together to get a map into R to the n. But a basic property of this Hamiltonian construction is that mu is constant, the Hamiltonian is constant on the orbits of the action. So each Tn orbit lies inside a fiber, and in fact the fibers will be completely consist of Tn orbits. So the fibers are Tn orbits. So what happens then is that over the interior of P, I'm using the notation that P means the closed set, over the interior of P corresponds to the free Tn orbits. So well, the picture over this interior is straightforward. The manifold is just a product, and we have this action. But then when we go to the when we go to the boundary of P, corresponds to, these orbits are all free. When we go to the boundary of P, the fibers are Tn orbits, but they're not free orbits. So depending upon in the actual sense, the codimension of the strata you're in gives you the dimension of the stabilizer. So, for example, in this two-dimensional picture, if you're on a vertex, this corresponds to the case where the stabilizer has got dimension 2. So the orbits are just points, the fixed points. The points on the boundary are not vertices corresponds to ones where the stabilizer has got dimension 1. So the orbits are just circles. So these are free over the interior. So you can sort of see the manifold being built up then by putting together these tori of different dimensions corresponding to the different strata of P. Again, the simplest case, you see, is the case of our sphere. Drawing it. So over the interior of this P, which is just an interval, we just take the product. So we think of taking a cylinder, and then we only have one other strata given by the points. So we just have a pair of points. So we're thinking of course, we can decompose the two-sphere topologically as the union of a cylinder and a pair of points. But we could do, a more complicated example would be to take, say, a triangle. This would correspond to the complex projective plane. So there we'd have so this is a real four-dimensional thing. We're thinking of that as built up as a product of this interior of the triangle times a two-dimensional torus. So we think of that over every point here. We imagine a two-dimensional torus. Over these edges, but not at the we're supposed to have a one-dimensional torus. So that's going to give just the same picture that we had here over each edge. So we're going to see for each edge we're going to see a picture of we're going to see a two-sphere, and we're going to have these fixed points the boundary. So of course this matches up with the obvious action. If we think of taking CP2 with the obvious action, so we think of Z1, Z2, we can act by essentially we can act by the two-dimensional torus sitting inside SU3, either diagonal matrices, unitary matrices of determinant 1. Then the fixed points correspond to the obvious things. We've got these three fixed points. And these three spheres we see correspond to the projective lines given by the equation Zi equals 0. So this is just discussing a sort of a topological picture, really, of how you visualize building up the manifold sitting over this polygon. What about supposing we want to reconstruct the symplectic form given this data, but over this interior P, if we take xi to be the coordinates on Rn, these upper indices, and we take theta I to be the coordinates in the circle directions, these lower indices, then on this product we take the standard symplectic form the sum of dxi wedge d theta I. And then we have to show that we can, when we collapse the fibers in this way, according to the combinatorics of our polygon, that we have to try to extend this thing smoothly as a symplectic form. But that's similar to the discussion we had before. So the third way we can think about things is more algebraic. This makes essential use of the fact that we have this line bundle around. The previous discussions, we didn't really need to have this line bundle. We could have slightly generalized the definition. So we're thinking of L as a positive line bundle. If we think about the algebra geometrically, that's to say, at least if we take, as general facts, if we take a high power of L, we'll have many holomorphic sections. In fact, by the Canara embedding theorem, if we take sufficiently high power of L, then those sections will give an embedding of our manifold in projective space. So in this approach, we focus on the sections of the powers of L. And if we put all these things together, we get a graded ring. So what are these in terms of from this point of view, what we want to do is to describe this graded ring in terms of our combinatorial data. We want to relate that to the polytope. So the basic point is that, of course, here we're not using the action because Tn acts. We can decompose into weight spaces under the action. So if in one direction, if we start with this given data, we can consider the action of the torus and consider how these things break up under that. In another direction, supposing we start with P in Rn, then we can consider for each k, positive integer k, we can consider kp into Zn. So what does it we want to say? So let's take the subset. Let's take the subset. Say A contained in Zn plus 1. It's the set of. So we take the first set of K and X, V, where V is in this set Kp into set Zn. So this thing forms a semigroup. The fact that P is convex means that if we have one pair inside here, and we have two pairs, and we take a convex we add them, then we get a third such pair. So we can write down a graded ring just by taking the sort of the semigroup ring corresponding to this. Or to say that, so that would be the kind of inverse construction. So to say what that means, conclusion, that's in a more clear way. What the conclusion is that each weight space has got multiplicity at most 1. Either a weight occurs or it doesn't, and the weights that occur for this power L to the k precisely correspond to the lattice points in this intersection with Kp.
Is it possible to see the weight spaces in this Kp? This A living? Is it possible to see the weight spaces in Kp?
Yeah, maybe I should explain this more. So what we're doing is we're going to a higher dimension. So so here at each level we have some set of larger and larger set of lattice points, and we're saying that this ring is just the ring corresponding to this semigroup. So in fact, the weights that occur for a given k are given by this intersection. So each weight in H naught extends the key with multiplicity 1, and the weights that occur correspond to points in Kp intersect Z to the n. So, for example, supposing we took the square. So this is P1 CP1 times C. This constructions behave in the obvious way with respect to products. So we take a product of two spheres, or CP1s, we get a square in R2. So these we've got 4 lattice points. Let's call it, say, X, Y, Z, W. They correspond in this picture to 4 points, say X, Y, Z, W here. And these generate this graded ring, pretty easy to see. But there's a single relation. These are generators. But there's a relation that if we take x plus w over 2, that's the same as y plus z over 2. So in this picture here, the x plus y is equal to, sorry, x plus w, the additive situation, is equal to y plus z. So multiplicatively, we get the relation xw equals yz. So that's just what that amounts to saying, is that we could construct this as a projective variety. It's embedded in by these 4 sections in CP3, but we have this relation corresponds to the equation defining it, which is just the equation of a quadric in CP3. Which is, of course, we know that that's what we get. So let's move on. We've got the last 10 minutes. This is sort of the global theory for how we, and really completely standard about how we pass from this kind of manifolds with an action to a polytope and back again. Now we want to consider the local differential geometry. So far we haven't. Our constructions are just encoding the Kähler class. They're not encoding the precise Kähler form that we are considering. So now let's pass to the differential geometry. So here, so we go back to these two points of view, the complex and symplective point of view, but as we started with. But one way would be to say we're going to take complex coordinates say so we're going to take our C, we're going to work on our C star to the n in X. So let's take our complex coordinates to be X of T. Wait a second. So TA plus I theta A. So this is going to be really a periodic coordinate. So we want to consider a Kähler potential phi, which is going to be in this coordinate chart, but we want a metric that's invariant under the rotations, that's to say the translations in these coordinates in the theta direction. So we want a function phi which only depends upon these t coordinates. So if we look at the d bar d, d bar of phi in the complex notation, that essentially corresponds to the Hessian of this function of n real variables. So let's write this as, to fit in the notation, let's write this with indices upstairs, phi AB, like that, to fit in with the notation we're going to use later. So in fact, what we're saying is that the metric, so omega, would be notation would be phi AB dTA d theta b. This is just what if we want to write. We have, so in this picture we have the standard complex coordinates. We have standard complex structure, but our differential structure is defined by this 2 form, which is given by this formula in terms of the second derivatives of this potential function phi. So of course, what these t's will lie on in Rn. So t is Rn. So we're considering a convex, the condition, this is a positive definite form of saying phi is a convex function. Studying from this point of view, these toric Kähler metrics is studying convex functions on Rn with certain conditions that we'll come back to, which guarantee that they extend smoothly to the x. So far we haven't built in our combinatorial data from our polygon. There's going to be some conditions involving that, which are the ones that give us a nice extension to the compactification. But for the moment, we're just thinking about the local situation. Or we can consider the symplectic point of view. So we're going to be working here on this open set int p times tn, where we have these coordinates x, did I write? X upper A, theta lower a, and now our symplectic form is standard. Omega is dxa d theta a, as we said. What we need to describe is the complex structure. From this point of view, we're fixing the symplectic form, and we're going to think of varying the complex structure. So that's, how can we parameterize that? We can parameterize that by saying that any compatible complex structure can be defined by a matrix, say ZAB, a complex matrix ZAB, with this, by decreeing that such things form a basis for the 1-0 forms. So Z is going to be a complex matrix, symmetric, and with the imaginary part of Z positive. And we're going to say if we have such a thing, then we can define, this is just sort of algebra at a point, we define a complex structure compatible with this symplectic form by saying that these things define the 1-0 subspace of the complexified cotangent space. So this is really the standard. This is what's called the Siegel upper half space. This is the standard description of Siegel upper half space. So anyway, such a matrix Z gives a way to parameterize the almost complex structures. What is the integrability condition? We're interested in integrable structures. Write that down. So the integrability condition. That's to say, if we write down, from one point of view, we write down the Nyhan-Host tensor for these in this notation for these almost complex structures, and equate it to 0, then this becomes saying that dzab dxc is this thing is symmetric in B and C. So since Z is symmetric, that implies that we can write, this implies two applications of the standard criterion for an exact differential. It implies that we can write Z so it's one application, ZIB is I dTA dxB, and then actually the TAs are dF dxa for some complex valued function f. So the integrability condition says that, in fact, the Zs that occur for integrable structures just can all be constructed out of a single complex valued function, f. On the other hand, we have an action of a group around. Supposing we have any function of the x's and theta's, that defines that generates a Hamiltonian flow. If we have, but we want to consider the ones that commute with the action. So if we have a function of if we have some function h of x, this defines a symplectomorphism which commutes with Tn. Action. So we can take one matrix value function z and apply a coordinate change, essentially, just changing the coordinates theta as a function of the x's, and get another one. And this will just take our function f, if you work it through, this will take it f to f plus sorry, so this will take z to z plus plus d2h dxa dxb. So what that means is that we can remove, by a coordinate change, by this coordinate transformation, we can remove the real part of this function, f, and so ultimately z we can reduce to the case when zab is I d2u dxa dxb for a real valued function u on P. So it's time to stop, but let's just sort of summarize what we conclude. If we take the complex point of view, then we get our geometric structure is encoded in a convex function on Rn, phi. If we take the symplectic point of view, then our structure is encoded in a convex function on this subset P in Rn, U. So, summary. Complex, considering phi, convex on Rn. And we wrote down the formula for omega. Omega is the sum of phi b dta d theta b. And I is standard. And the complex structure is standard. If we take the symplectic point of view, then we have U as convex on, well, let's say, the interior of P for the moment. We haven't discussed simply the boundary. So omega is the standard form. But the complex structure is given by the formulae above, or perhaps it's simpler to say in terms of the metric. G is equal to sort of U AB dxa dxb plus, if we write UAB for the inverse matrix, d theta A d theta B. This means the inverse. So that's a place to stop. So we have these two different ways of setting up the differential geometry on a toric manifold, both in terms of convex functions. As we'll recall in tomorrow's lecture, the relation between these then is something very classical given by the Legendre transform. For going from one picture to the other. Okay, but I shall stop there for today.
Can you do it in an arbitrary compact toric manifold, or does it have to be projected?
So, whether you could do this for non-compact? Is that the question?
No, for compact, non-projected.
Yes, I mean, you mean if you don't have this line bundle? You mean,
yeah.
Yes. That's yeah. The only if you relax the condition about having integral vertices.
Right.
Yeah, I'll give an example of that tomorrow when we consider blowing up a point.
They're still projected manifolds. It's just that you can get Taylor classes on them that aren't integer classes.
So they're still projected.
They're still projected. Simon, you had an overarching point of view about the formal complexification of this symplectomorphism group, and I guess that the capital F here is playing the role of.
Yeah, exactly. That's what we're saying in that term, is that all our integrable structures are in a single orbit of this complexified action. So F is a complex. So this is the real functions give the real symplectomorphism group in this context, the things that commute with Tn. But because it's just the space of functions under addition, you can complexify. And this integrability discussion is saying that essentially you lie in the same orbit. But of course, you don't. It's background, but you don't need to think about that in terms to write down the formulae, of course.
Any other questions? Oh, let's